Welcome to the second video for stress combinations. In this one, we'll begin a second example, one that involves torsion and moment and shear, all in one example. And we'll look at a couple of different points on that cross-section and the stresses that it's going to be experiencing. Now let's consider this problem. It is sort of the go-to for this topic. I'm sure you'll see it in any given textbook you're looking at or any other reference materials you might hunt down. It is just an elbow, a circular cross-section fixed at A with a corner and a simple load at this end. Maybe it's angled, we could have that. That would be a little bit more complicated than what we have right here, where we have 10 inches in the x direction, then 4 inches in the y direction, followed by a -5 kip force in the z direction. And this is our cross section. It's just a circle, just a solid circle. And so we want to know, what is the stress state at these 4 points at the top, bottom, and two sides of this circle. So the first thing that I usually do in these problems is I consider, okay, so we were looking at these 4 points and we're looking at them at point A. And if we're doing that, obviously we've got all of our stress equations that we need to consider. So let's list out all of our stress potential sources. So we've got normal stress from a normal load. We've got normal stress from bending. We've got shear stress from transverse loads, and we've got shear stress from torsion. And we need to think about all 4 of these to determine what the stress state is for any given point. And they're going to be different for different points, because remember, if we want to know the normal stress on that previous problem, well, the normal stress was constant, but the bending stress was a function of how far we were from the neutral axis of the original problem. Right? The transverse stress, well, the stress, this is going to be a function of our shear flow, or our shear flux. It'll be a function of Q, the first moment above it, so that's going to be changing as we move from D to E and F back to G. Torsion, that's going to be a function of how far we are from the center of the circle itself. So all 4 of these have a different distribution of stress, and so they're going to be different at all 4 of those points. So let's get to work determining things that we can use generally. Because if we are looking at point A, which is to say we're looking at this end, then we can determine that the axial load P, well, that's going to be 0. There's no axial load applied here. So we got that going for us. We can also determine that the moment, the bending moment, is going to be equal to -5 kips times 10 inches. Because remember, if we're looking for moment about the y-axis, right, that's what this is, moment about the y-axis, then this distance we have in the y direction, it don't matter. So that'll be negative 50 kip inches. I like to think about, because of the curvature it's going to bend it in such a way that's going to cause negative moment. All that really means that we need to remember, and it's important for us, is that at point A, the moment induced by this force is going to cause us to have tension at point D at the top and compression at point G on the bottom. Then we have the transverse shear, V. That's just going to be the full 5 kips. And our torsion. Well, our torsion, that has to be our moment about the x direction. Remember, that's just how that goes. So torsion about the x direction, that's going to be our 5 kips times our lever arm here, which is 4 inches, which is 20 kip inches. And we just need to remember that it's being twisted counterclockwise. Okay, so now we've got those all determined. We do need to figure out the rest of the things, because in the end, our goal is to use these equations. One for normal stress, which is that it's P over A. One for our bending stress, My over I, the moment times the distance from the neutral axis, divided by the second moment. We want to use the shear stress, which will be V times Q for I times the thickness. And we want to use the torsion equation, which is T times our distance from the centroid divided by J, our polar moment of inertia. Now, fortunately for us, when we're doing this problem, we have, we want to know the second moment of inertia, xx, which is going to be it's going to be the integral of x squared dA, right? And we are going to want to know J, which is really IXY. It's the integral of x, y, dA. For a circle, they're going to be the same. How convenient. So the second moment of inertia about the centroid of a circle is going to be the same as the polar moment of inertia. That's very convenient for us. So that gives us that the x direction. If we had bent, we could also have had bending about the y direction as well if we had a load applied, in this direction, or that would give us moment about the z direction. We have moment about the x direction, that's torsion. So that's going to be equal to, J is going to be equal to pi over 4 times our radius to the fourth, which is going to be 0.75 inches to the fourth. Is going to be something that I don't have memorized. 2.4 8 inches to the fourth. And we're similarly going to want the area, I guess the area is going to be pi 0.75 inches squared, and that's going to be 1.767 square inches. So now we've got the loads from the reaction today, and we've got the second moment of inertia, the polar moment of inertia, and the cross-sectional area. We can begin to implement these 4 equations. So let's look at, let's look at point D first.